As we get set up for our next finalist, I wanted to call up, so Dr. Moss, could you come up here? I'm going to bring up our head judge. Give you a microphone here, dear. So you've been involved in the Young Scientist Challenge for the past several years. Tell us about this. Did you have any experiences like this when you were younger?
Well, when I was younger, I did science fairs and loved science fairs. And as a teacher, I coached Science Olympiad, but nothing is like the 3M Young Scientist Challenge. These young people, I mean, the opportunity they have, the people that they get to meet at 3M, every one of their mentors are just amazing people who could end up in the Carleton Society, winning Nobel Prizes, that kind of thing. These kids have amazing experiences, and there is no competition like the 3M Young Scientist Challenge anywhere.
What about their communication skills?
And that's another thing that's really different about this competition than any other. It's not only about how much science, technology, engineering, and math they understand, but it's how well they communicate, how well they work with other people, how they put it all together.
Yeah, we were at lunch and we were talking, so we're surrounded by, you guys are just absolutely brilliant. You're an inspiration to the kids that are watching, honestly. Because at lunch we were talking about taking a banana and putting candy corn on it to make it look like a piece of corn on the cob. And it took us like 20 minutes debating how it would work. So the work that you're doing is significantly more impressive. So kudos to all of you.
Yes.
What's been your favorite part of the week so far?
My favorite part is always getting to know some of these students and seeing what they're doing as well as what the mentors are doing, because it gives me hope for the future. As we think of all the problems that we need to solve in the world, I feel like there's many people in this room who can help come up with solutions for those problems.
Excellent. Let's give Dr. Moss a round of applause. Thank you for leading our judges. Are you ready to go? You guys ready for our next finalist? All right. So Mythri is from California, and she is going to wow and impress you. So Mythri, all set?
Yep.
Take it away, my dear.
Thank you. So, one car produces 20 pounds of carbon dioxide per gallon of gas, or 200 pounds per week. So one car produces as much carbon dioxide in a year as the weight of an elephant. And one tree absorbs only 50 pounds of carbon dioxide per year. So this means it takes 208 trees to absorb the CO2 from one car. And there are 100 million cars on the roads just in the US. So absorbing even 5% of the carbon dioxide from one car would be equivalent to 10 trees. Since automobiles are the primary consumers of carbon dioxide, I created a device for automobiles called CARS, or Carbon Dioxide Absorbing Retrofit System. My favorite movie is Apollo 13, not only because it's really thrilling, but also because it shows many aspects of innovation. So my favorite scene in this movie is when the NASA scientists have to come up with a carbon dioxide filter on the spot to save the lives of the astronauts. So I did some research and found out that lithium hydroxide is used to filter carbon dioxide in space shuttles and submarines. However, lithium hydroxide is very expensive and is definitely not available to students like me. So I used the periodic table, and I found elements for hydroxide compounds in the same region of the table as sodium and as lithium. So I selected potassium hydroxide, sodium hydroxide, and calcium hydroxide, all of which are in the nearby groups. I also found out that ionization energy decreases as you go down the periodic table and as you go to the left. So I hypothesized that potassium hydroxide, which is the farthest to the down and to the left, would be the most effective and fastest reactant with carbon dioxide. So here are all the materials I used. As you can see, 3M products were basically the life of this project. So while designing my prototype, I used Google SketchUp, and I had three main considerations. It should withstand high temperatures, not block off the exhaust, and not be heavy. So here's my first prototype. It was made up of a simple metal elbow connector, which looks like this, containing aluminum wire mesh filters, and they were coated with these hydroxide compounds. So I tested it all, assembled everything together, and guess what? It failed. No surprise. So now my second prototype, I replaced the aluminum wire mesh with filter bag cloth made by 3M, since the aluminum filters were partially dissolved by the chemicals. So this time I was hoping that the bag cloth would be more resistant to the chemicals. But I tried it again, and guess what again? It failed. So I looked at it again, and this time, the filter was blocking off the exhaust, causing the temperature to increase, which is really bad for the car and is very dangerous. So I redesigned my prototype, and I created 2 new designs this time. So first, I created, using the elbow connectors again both times, I used 3M automotive fuel filler hose made up of fluoroelastomer and 3M automotive fuel line hose made up of epichlorohydrin. And so for the first design, I had the fuel filler hose in the center surrounded by fuel line hose. But for the second one, I had only fuel line hose. I replaced my filters also, and this time I used 3M coated filter fabric and 3M Nextel ceramic fabric. But they were still too thick, so I removed threads from them using tweezers to create air passageways. So here's how my design was assembled. I basically had the designs in the center and the filters for the first design on the outside with a metal clamp holding it down, and on the back side I had a second filter with a ring on the metal ring on the inside with the filter on the covering it. So here's how I tested it. I coated all my filters with the hydroxide compound separately and attached them to the device, assembled everything, placed my CO2 meter right here at a set distance away from the car and connected it to a laptop USB port. Then I started the car and launched a CO2 Sense program to provide an accurate graph of the CO2 change over time. I confirmed all my results at a local smog check station. My independent variables were the type of absorbent, filter fabric, number of filters, and device design, and the dependent variable was the amount of CO2, and I had a lot of constants that were constant for all the tests, and I used a control setup of distilled water filters. So here are my results. This design was much better than the first design because the first design blocked off air supplies partially, and my second filter was worse because the surface was too smooth and did not allow the chemicals to adhere. And finally, potassium hydroxide absorbed CO2 the fastest. But however, CO2 was absorbed so fast that the filters were absorbed so quickly, so it would be more practical to use calcium hydroxide, as I demonstrated through a PS test. It lasts longer, and it has a good absorption rate. So in the end, my device, CARS, has been proven to be effective, and it is definitely feasible. And by using this, problems such as global warming, which have even been led to water shortage, can be prevented.
First off, thanks for the very elegant beginning. I love it when you make something very accessible with the tree-car comparison. I thought that was a really good way to explain it to somebody who doesn't know what's going on. Secondly, I would just like to know, how long did you run these tests to see if there was any impact on the car? Did you do it over a long period of time?
Yeah, at the smog check station, I ran it over a long period of time. But at home, I mean, so much increasing levels of carbon dioxide and whatever else is coming out of the exhaust is not good for me or anybody in the general vicinity. So I ran it about like 5 minutes max idling time, but I did it multiple times. So I was able to see how the number of times I tested it and how long I tested affected the car. So they went in waves. So as over time, it went up, and then it went down, and it went up, and it gradually leveled out.
Can you walk me through exactly what's happening on that poster, how much absorbance is needed, and what you did there?
This one?
Yes.
Okay, so I used stoichiometric calculations. So using the molar masses and the molar ratios, I was able to create a ratio and proportion of the amount of carbon dioxide absorbed by each chemical. So for example, lithium hydroxide, though I didn't use it, I used it to compare. So using all the atomic masses of all the elements in it, I found out that its molar mass is about 48 grams for the amount that I was using. And then the carbon dioxide amount it absorbs is 44 grams. So using that, I was able to find out that 100 grams of the lithium hydroxide absorbs 91.6 grams of carbon dioxide. So I did similar calculations for all the other chemicals, and then using that, I was able to compare them and at least form my hypothesis, confirm my results afterwards.
Okay, the reason I asked that is because on your third question there, it doesn't see, on your third equation, it doesn't seem like that adds up with conservation of mass, because I don't, that's maybe I can't see the numbers, but I don't think those add on both sides to the same number.
So you mean like?
Yeah, 74 plus 44, I don't think is 106 plus 18.
Some of the gases can escape during the absorption of the carbon dioxide, so not all of it is present, and then some of them are converted into sometimes oxygen. There's the numbers I noticed at the smog check station. It just barely increases and decreases by small decimal amounts.
Okay.
You highlighted at the beginning that for example, 1 gallon of gasoline that's been combusted can generate, you said, approximately
20 pounds.
20 pounds of CO2.
Yes.
So my simple mathematical calculation, if I have a car that has 20 gallons of gas, obviously that leads to up to 400 pounds of CO2.
Yes.
How do you imagine placing this, for example, on an automobile, where now you generate not only that amount of CO2, but all the byproducts, and now you have to address the additional weight associated with all of that captured CO2. How will that impact the environment?
Can you repeat that again? It's slightly different.
Sorry, it's a long question.
Yeah.
In a nutshell, you're capturing a very large amount of gas in the form of additional weight, for example.
Yes.
So it could be up to, say, 400 pounds for a 20, plus whatever other byproducts. How will that impact the environment?
Okay. So, well, first of all, the filters, once they contain the carbonate products, they can be dissolved in water, and that converts it into some stable form that can be easily captured, and then that dilutes it. You can use like vinegar to neutralize it, and then flush it down the sink or down a drain. And so you can reuse your filters multiple times through that method, but the filters would have to be replaced quite often. So that was one of the things I would like to do in the future to increase the longevity. But the biggest thing is, most of the products that exist now, you have to replace the entire filter. But for me, it's only you have to replace the entire device. But for this one, it's just the filter. So you just have to pretty much insert and take out the filter, which is quite cheap.
What were some of the challenges that you encountered in developing your prototype?
The major thing I encountered was that first I tried this filter, which is 3M filter bag fabric, and it was so thick that it blocked off the exhaust, and it just got really bad. And after that, I tried those two, but they were still too thick, so I pulled out the strands using the tweezers, and that created some air passageways to flow through. And another thing was, when I was starting my experiment, I was using my dad's car because it's quite an old car, and it's easy to see the difference between the carbon dioxide levels because it produces quite an amount of toxic gases. Okay.
That was fantastic. That was fantastic. Just as a side note for the folks that are watching at home, the students who are watching, and you ask the question, why do I need math? This is why you need math. That was so fantastic. It's a language, right? It's a language we can use to solve problems. And your conversation with Peyton, like, I was sitting there in awe. I was going to jump in a little bit, but it seemed like you guys had it under control. But let's give Mythri another round of applause. Nice job, dear.